Okay, so let's get started. So today we want to finish chapter 2, and we discuss some graphics in R. Then if we have time, maybe we go to chapter 3. Chapter 3 of Stat 5030 materials for chapter 6 and 11, and also discuss some more details of how to deal with the problems in linear regression. Okay. So do you have any questions from the previous lecture or quizzes? Okay, so if not, that we start chapter 2, and the chapter 2 slides have been available, and the chapter 2 lab slides are also available in Canvas, and also chapter 3 slides are available as well. Okay, so I will share the screen of my iPad. Yeah, so the last time that we finished this slide, so bias variance trade-off. So once we observe the errors, expected the size of errors, then that can be decomposed into this squared bias and the variance of the estimate and the so-called irreducible error. So we have 3 terms. So this term, this term, and this term. And yeah, so actually the one quiz from today is from this slide. So once you observed f hat, we cannot really once we observe f hat, so the f hat is observed. So this is estimated the value of y. So we can calculate this, but we cannot observe this f naught and epsilon. So in reality, we cannot really decompose these 3 from the real data. But at least conceptually, we have the 3 terms: the square of bias and the variance of f hat and the expected size of epsilon squared. And the last one is so-called irreducible error, so that we cannot really reduce the size of this. So just the first 2 terms are important, and usually we have the trade-off between these 2 terms. And so the implication is that to minimize the expected squared error, so that is the left-hand side of this term, equation. Usually we have to balance this first term and second term. So the third term is not observed and also constant. And roughly speaking, more complicated model, more complex model has smaller bias, but large variance. And the simpler model the bias is larger and the variance is smaller. So we can tell this because maybe just because of the example we covered last time. So we make a guess on someone's height based on the foot size. And if we have the 5 observation already, the 5 pair of foot size and the height. And if we observe a new observation, with whom the only foot size is available, if we choose just the closest foot size of the original sample, we can estimate the new person's height more accurately, but since it is based on only one observation, we have large variability. So we have small bias, but the large variance. But if we use simpler models, for example, just take average of the 5 existing people in the sample, then the bias is larger because the new person's specification does not match just average of the original 5 people. But the variance is smaller because we make a decision based on 5 observations. So generally, the complex model, smaller bias, larger variance. Yeah, and there is trade-off between bias and variance. Maybe this is more intuitive example to explain the relative size of variance and the squared bias. So the fitted line, so okay, so at first, these black circles are observations. And the black solid line is the truth. So observations are truth plus minus error. I mean, plus error, plus epsilon. So it's, okay, so yeah, so it doesn't say anything, but so black circle, so these are observations. And the black curve, this is the truth curve. So I would say the observation, so true curve, okay, so maybe larger place. So observation is basically y. So y, that is equal to f of x plus epsilon. And the true curve is the y is equal to f of x. So since observation have some error, so we have some fluctuation, the plus f of x. And the other 3 lines are fitted curve. So I would say this is f hat. We have 3 kinds of f hat, maybe f1 hat and f2 hat and f3 hat. And you can see that at first, probably the blue curve is the best. You can see blue curve is closest to the black line most of the time. So if you pick up specific point, maybe other curves are better. For example, the yellow curves are better at this point, and maybe green curve is better than blue curve at maybe where? Maybe at this point or something. But the mostly blue curve is closest to the truth, the black curve. So what's the situation here? So yellow one is a straight line. So this is too simple to estimate the black curve. So this is actually just a straight line. So in this case, actually the bias is large. You can see that, for example, that we want to calculate the fitted value at 70. We have large bias, large negative bias here. But instead, this yellow line is probably very stable. If we add some data points or we remove some data point, some observations, probably yellow line that doesn't change much because the yellow line is so simple. If we remove, even if we remove several observations or we add several observations, it does not change. So bias is large, but the variance is small. And green one is the other way around. So it has a larger variance, but the smaller bias. So since the blue one fits, I don't know what is, sorry, the green one. Green one is the curve that fitted by the polynomial of degree 10 or 20. So it is a very complicated curve, and it's affected by each of the observations. So the bias is small. So it basically adjusts to every value of x. Not every value of x, but the many value of x pretty flexibly. But this is the unstable. If we, for example, remove this observation, probably this green curve becomes smaller around maybe x is equal to maybe 25 to 30. So it's very unstable. So removing 1 point or adding 1 point change the curve a lot. And the blue curve is a good one to balance between bias and variance, so that it approximates the black curve best. Sorry. Yeah. Okay. So we have to balance between the large the size of the squared bias and the variance. Yeah, so this is the conceptual explanation of variance and the squared bias. So again, the variance and the bias are not observed in reality, but this is the simulated data, so that we can see the true f of x. So that's also the true epsilon. So we can measure the size of variance and the size of squared bias. And we have to balance between two quantities to get the best estimate. Yeah. So this is the regression part in chapter 2. So do you have any questions? Yeah. So details about the estimation in linear regression will be covered in chapter 3 as well. Okay, so next we go on to the classification. So a measure of error for classification problems we have to define. So the regression problem, usually we minimize the sum of squared errors. So, or maybe square root of the mean square errors. So that is fine. So basically the sum of, we minimize the sum of epsilon I square, maybe epsilon I hat square to be exact. So this is for regression problem. So how about classification problem? Classification problem, we have just categories. We have category maybe ABC, and we have category ABC. Okay, so our prediction and the truth. So this is maybe the truth, and this is predicted. So we have the contingency table such as this. And you can see if this contingency table is obtained, then you can see that for most observations, our prediction is correct, because the truth and the predicted category are the same for most observations, 25 observations out of maybe 32. But how to calculate how to define this kind of the measure of error? And the easiest one is just error rate. So we count the number of errors. In this case, we have 7 errors, 1 plus 1 plus 0 plus 2 plus 1 plus 2. So we have 7 errors out of 32 observations. So we have the 7 over 32. So this is basically the so-called error rate. So if we use the notation y sub I, this is the truth, and yi hat, this is predicted category. Then if this is not equal, then we give 1. And if equal, then we give 0. Then we take summation and divide by the sample size. So that is error rate. Yeah. So yeah, this is the one simplest way. Yeah. So, but in regression problem, we have the problem of training error and test error. So when we minimize training error, usually we make the too complicated model, because our criterion is ad hoc. So if we know the data, if we use more complicated model, then we can explain more. So if we use unnecessarily complicated model, then usually the training error is smaller. And in classification problem, it's the same. So error rate is extremely small if we develop the training. Error rate is extremely small if we use the complicated model. So in reality, we have to use the validation approach. So we prepare training set and test set, and we determine the model with the training data, training set, and we evaluate the error size with the test set or test data. So that is conceptually expressed as expected value of this error rate. So a good classifier is the one that the test error, not text, test error is smallest. Yeah, so do you have any questions? Test errors, yeah, that is a natural one. And of course, we can define other type of errors. For example, if in this example, we have category A, B, C, but if this is ordered, so A is better than B and B is better than C, then you can see that the this one and this one are more serious errors than the other orange ones. Because the A and the C are totally, maybe we should give a larger penalty on these green ones. So that is called a weighted kappa in diagnostic medicine. Weighted kappa. Yeah, so such a criterion is possible. But if these categories A, B, C are just different categories and no orders and no distances, no distance between each pair of points, then we can use the just error rate. Yeah, and okay, so now the when we developed the estimation model, how to make this table? So suppose we have some data set and we developed a model, then how to define, how to obtain this table from the training set or test set. And the easiest way to get this table is the base classifier. So basically this gives the so the model decides the class based on the largest probability. So maybe we start with one example here. So that we want to develop a model to see a person is either a child or adult female or adult male. And we have to determine this only based on height. So maybe we have a large number of people entering the train station, something, and we have to decide, we have to judge if a person is either a child or adult female or adult male. Okay. And suppose that these probabilities are given. If height is less than 145 centimeter, that person is 70% child and 20% adult female and 10% adult male. Height is between 145 and 165, then the probabilities are 20%, 60%, and 20%. More than 165%, they're 0.1, 0.3, 0.6, 10%, 30%, 16%. And given height, how to decide whether a person is child, adult female, or adult male? And the rule, the base classifier is based on the largest probability. So this one, and this one. If the person is less than 145 centimeter, that we decide that that person is probably a child. And between 145 and 165, that we decide that the person is an adult female, and more than 165, then adult male. So that is the Bayes rule, a Bayes classifier. So if mathematically express this idea, suppose that the conditional probability of y given x naught, so that this probability of y is equal to j, where j is either 1, 2, 3 up to g. G is the number of classes, and the x naught is the value of the variable x. Then the best classifier is to assign each observation to the most likely class. So this is called the Bayes classifier. And the error rate for this classifier is called the Bayesian error rate. So given x, the Bayesian error rate is this. So if we, we have this. So if we have the 70%, 20% and 10%, and we choose this category as our predicted value, we make 30% error. So we have 20% probability that the truth is an adult female, but we regard that person as a child, and 10% error for adult male. So 30% error. So if mathematically express this idea, so this becomes this. So 1 minus the probability that we assign the correct class. So 1 minus 0.7 is 0.3. And of course, this Bayesian, or this one, to get this one, we need the probability of getting person less than 145 centimeter and between 145 and 165 centimeter, and so on. So we have 3 cases. So if this is that 50%, 25%, 25%, we have to multiply these weights with these error size. And if these proportions are different, then error rate is different. Expected error rate is different. So we need the distribution of x to see the expected error size. But the given x value that we can determine the Bayesian error rate. Yeah, we have one quiz from this Bayes error rate and the Bayes classifier. Do you have any questions?
Yes. So Bayes theorem from probability, it's like probability of like
your mic is off.
Oh yeah. So the Bayes theorem from probability is like probability of A given B is the probability of the intersection divided by the probability of the one that's given, right? And I see that we're calling this classifier the Bayes classifier, but do we ever actually use the Bayes theorem, or is it just called Bayes classifier because we're dealing with conditional probabilities?
Sorry, your voice was interrupted for 5 seconds. So sorry, can you repeat the question again?
Yeah. So we know like Bayes theorem from probability is like probability of like A given B equals the probability intersection divided by the probability of B. Yeah. So we know that that's Bayes theorem. So my question is this called so like this classifier that we're using here? We call it Bayes classifier. Is the reason why we call it Bayes classifier just because we're working with conditional probabilities? I haven't seen here where we actually use Bayes theorem.
No, I think that probably it's not directly related to Bayes theorem, but generally the Bayes statistics is considering the distribution given some information. So in this case, the given x, we have the distribution of y. Y is the response, and in this case, if x is less than 145, then we have this, the distribution of y here. So distribution of y given x is usually the Bayesian approach. So probably that's why we say the Bayesian error rate, and not directly related to Bayes rule.
Yeah, so it has more to do with the fact that we're dealing with conditional probabilities than actual like Bayes theorem. I gotcha. Thank you.
Yeah. Any other comments? Questions? Yeah. Okay. And so actually the last year, maybe 2 years ago, the one student make a presentation, and she tries to classify the athletes to sports. So basically, she used the Olympic data or something, and there are maybe 20, 30, maybe more than that, maybe 50 the different sports. And she developed a predictive model that to assign each player to the sport. So given the specification, for example, if someone is maybe 5 feet and maybe 6 inches, and the weight is 250 pounds or something, then maybe he or she is a weightlifter or something like that. And the prediction performance is like maybe 15% correct. And she said that it's a low probability for success, but actually probably that probability is pretty high, because we have 50 the sports. So if we randomly assign it, then only 2% correct rate. So the correct rate, the Bayesian error rate really depends on the number of classes. So character recognition problem, if possibility is either A or B, then it's much easier. But if we have 26 characters, it's harder to categorize letters correctly. Yeah, and the binary case. So binary case, if we adopt the Bayesian the Bayesian classifier, basically we judge based on the probability of, okay, so suppose Y is binary, so Y is either 0 or 1, then a Bayes classifier is Y is equal to 1. I mean, Y hat is equal to 1. If probability of Y is equal to 1 is more than 50%, and Y hat is equal to 0 if probability is less than 50%. Maybe equal to 50%, you have to include the either of these two cases. And yeah, so this is one approach. Sometimes you want to use the difference threshold, because for example, if all estimated probabilities are less than 50%, this classifier does not make much sense. So at times that we choose different classifier than Bayes classifier, but if we use Bayes, 0.5 is the boundary. Yeah, this can be done, for example, by logistic regression. Maybe we will cover it later, but the logistic regression is the model to predict probability of Y is equal to 1 given the value of X. Yeah, so yeah, so this is just one example of the Bayes classifier for X2. So we have the X1 axis here and X2 axis here. And which one is which? So we have two classes, orange and blue. And the circles are observations. So these are observations, these are observations. And yeah, either way is good, but yeah. So suppose that this is class 0 and this is class 1. Then based on some model, we can calculate the probability of each possible point gives Y is equal to 1. So maybe this probability is maybe 0.6, and this probability maybe 0.4, and this probability maybe this point gives the probability that Y is equal to 1 is equal to 0.1, and so on. Then this boundary is the probability of 0.5. So probability of Y is equal to 1 given X is equal to 0.5. And this boundary that gives basically the decision. So if the points are upper left side of this complicated curve, then we decide that these points belong to the class 0. And if the points are around here, then we decide that these points belongs to the class y is equal to 1. So yeah, just one example. And this is, I think, the boundary based on the so-called the nearest k-nearest neighborhood methods. And I would explain this idea. So k-nearest neighborhood method is a non-parametric approach, so data-driven approach to estimate the conditional probabilities. And the rule is pretty simple. So I think that this equation is somewhat confusing, but okay, so we take the 3 closest point, or in general, k closest point to each possible point, not observed point, but each possible point. And out of the 3 closest points, the 2 of these are blue and the 1 of these is orange. So we decide that the probability of blue, so given x, is equal to the 2/3, and the probability of orange plus 0 given x is equal to 1/3. So this is the so-called nearest neighborhood method. Yeah, so if we use the formula, it becomes this. So probability, okay, so in general, we have some natural number k, and we have several classes, maybe j is equal to 1 to g. Then we estimate the probability of y is equal to j given x is equal to x naught is equal to 1 over k times the summation of indicator variable of yi is equal to j. So this is basically okay, and the I is the neighborhood of this x naught. So n naught is the set of k points closest to the x naught in training data set. So that means basically that we count the number of points in this neighborhood which have the label j. Then we divide this by the total number of observations. Then that is the probability, estimated probability of y is equal to j given x. So in other words, the KNN estimates the probability by empirical results of k most similar cases. So probabilities are different from empirical ratio. Right? So if you are not successful that when you bought the lottery tickets in the past 2 years every day, so 730 cases, but that does not mean that your success probability is 0 for the next try. So the probability and the empirical ratio are different quantities, but we basically approximate the probability by this empirical ratio. That is the KNN. Yeah, so if we use the criterion, then the boundary is this black line on the right pane. So you can see, for example, so suppose that we want to calculate the probability of blue and the probability of orange at these 3 closest points. I think it's a little bit hard to see. Probably, so this is the closest, and this is the second closest, and on the boundary. So if we go a little bit to this direction, then this is closer. So 2/3 orange, 1/3 blue. But if we go the other way around, then this point is 3rd closest. So 2/3 blue and 1/3 orange. So that's why we have this point on the boundary. So of course, if this point, the closest points are this, and this, and all oranges. So this point belongs to the region of orange area. So this boundary is pretty complicated, and yeah, This is a zigzag line. And these are the three results of k nearest neighborhood methods with different k's. And this is k is equal to 10, and the center one is k is equal to 1, and the right hand side, this is k is equal to 100. I think that yeah, my slide maybe delays for 20 seconds. Yeah. Okay, so yeah, okay, so we compare. So what's the difference between these? So which ones are most complicated? So which boundary is most complicated, do you think?
K equals 1.
Yeah, k is equal to 1 is the most complicated. So anyway, so these are not smooth line, but the k is equal to 100. This is closest to a straight line, right? And k is equal to 1 is affected by just the closest point, just one closest point. So it really depends on each observation. So we can say that the k is equal to 1 is more complicated model, or we can say large variance, small bias and large variance. Yeah, and k is equal to 10 is in between. And actually, this purple, the dotted line is the true boundary between these two. So this is this simulation-based data, so we know the true boundary. And which the boundary, which the black line is closest to the purple dotted line. And you can see that the k is equal to 100 is too simple. I mean, black line is too simple, and k is equal to 10 looks the best. K is equal to 1. It looks too complicated boundary compared to the truth. So probably that this k is equal to 10 is the best one. Sorry. So k is equal to 10 is the best one. Yeah. So we have to optimize k in some way. So usually we use the test training and test approach. So we train the boundary by training set. Then we calculate the maybe error rate with the test set. Then we can optimize the number k. And this figure, you can see that the horizontal axis is 1 over k. So that means the 0.01 means k is equal to 100, and the 0.1 means k is equal to 10, and 1.0 is k is equal to 1. 0.5, k is equal to 2. 0.2, k is equal to 5. This is k. Yeah, so training set, training data, with training data set, the error becomes smaller and smaller as k gets smaller, or 1 over k gets larger. Yeah, so data has some fluctuation. So the sometimes larger, sorry, the even smaller k, the test error gets, training error gets smaller. Training error gets, sorry, the training error gets larger, even k is smaller. But as a tendency, it gets smaller and smaller. So smaller k is best. obviously k is equal to 1. We choose the observation itself, so always it's correct. So we see specific, the x n, and the one nearest neighborhood is based on this, the yn itself. So always it's correct. So yn is equal to 1, then the yn hat is equal to 1, because we judge based on just one observation. Yeah, if we don't have any ties for xn's. If x1 and x2 and x3 are the same, still we can make a mistake, but if no ties, then this is always correct. But the test data set, test error is minimized at some certain range, probably around here. So k is equal to maybe 15 to k is equal to maybe 8. And larger k, the smoother boundary. So probably around here. So k is equal to maybe 15, or around 15. This is probably the best value of k. Yeah. So pros and cons of small k and large k is similar to bias variance trade-off in regression problems. So small k means small bias, large variance. A large k, smoother curve, large bias, but the small variance. So the meaning of bias is less clear for classification problems. So if we see the fitted probability, then we can see the fitted curve. So we can see the bias is large, but if we only see the actual label is a 0 or 1, it's a little bit harder to see what's the bias. But basically, in terms of fitted probability, that we can define the bias. And conceptually, at least, we can say the large k means large bias, but small variance. Yeah, so this is chapter 2. And also, I want to mention that the k-nearest neighborhood method can be applied for regression problem as well. So we choose for example, the 5 closest observations, then take average of y values, then that is fitted value of y. So we can use k and n for regression problems also. Yeah, but just for classification problems, we haven't studied any models except for maybe logistic regression. So just I discuss one method, k and n, for classification problem. Any questions? Okay, so maybe yeah.
Oh yeah, sorry. So if we're doing k nearest neighbors for the regression case, is there ever a time where instead of taking the average y value of the k nearest neighbors, maybe you put a higher weight on the one that's the closest, then you put a lower weight on the ones that are further away, even within the k nearest neighbors, or do people usually just take the average?
Usually the average, for when we say k and n, it's average. And if we give weight, probably we say that as a local regression. And local regression is more general idea, but the local regression give weights, so based on distance. So if distance is closest, then we give higher weight. Distance is larger, then we give lower weight. But here the k and n's idea is just taking average or taking the proportion, right? So taking average means that we fit the constant, right? So in terms of regression, that we fit the y is equal to just alpha plus epsilon. And this alpha can be, more complicated quantity. For example, alpha naught plus alpha 1 plus 1 times x1 plus alpha 2 times x2. So this is the so-called local regression. But if we only use the intercept, we say still we can say local regression. And if weights are all the same, we can say k and n.
Gotcha.
So maybe we can say KNN is special case of local regression with constant. And this is also the special case of local regression. Yeah. Yeah, that's a good point. Yeah. So any other comments from other students? Yeah, maybe, but still, I'm not an expert in KN, so I'm not necessarily able to answer questions. Okay, so now that maybe we switch to my PC, I mean my MacBook, to explain some chapter 2 lab slides. So I share screen. Yes. Yeah, so just this is a kind of introduction to use R, but I think all of you are somewhat, at least somewhat familiar with R. So just I discuss some graphics in R. Yeah. And the one thing we haven't discussed in the 5030 or 6840 is the 3D graphs. So I discussed the 3D graphs first. And also I discussed some plots, such as the box plots, and also the some pairwise plots, and some heat map for correlation metrics, and some others. So that is this chapter's topic. It's pretty short. And the textbook has some more materials. So at first, the contour plot that we can make. So suppose that x is 1 to 10, y is 1 to 10. So just the 1, 2, 3, 4, 5, 6, 7, 8, 10. So 10 elements. So we define the function x squared plus y squared. So this is parabola. And the g is equal to more complicated function, cosine y over 1 plus x squared. So it's a periodic function with respect to y. So the period is 2 pi, and x is large, value is much smaller. X is also large negative value, I mean negative 100 or something, then the value of g is small. And if we want to see the contour plot, then we can use this at first, that we define value of f. And this is a convenient function. So outer function x, y, f. So we evaluate this function f for all combinations of x, y, all pairs of x, y. So x is 1, y is 1, x is 1, x, y is 2, and so on. And x is 2 and y is 1. So we have 10 by 10, 100 possible numbers. And we can calculate the f of xy at once by this way. So fxy is 10 by 10 matrix. So G, the same. And the contour plot, then we can make this. So it's a little bit complicated, but it's overall written by the contour plot of G. So contour plot of f of x is these curves. So this is just the circular. You know, you can see the scale of x and y are different. So it looks the ellipse, the part of the ellipse, but like this. So this is the contour plot of y is equal to f of xy. And g of xy, these ones. So these ones. So it has the period of 2 pi in terms of y. You can see that this is peaked at maybe pi. This is peaked at maybe the 2 pi and 3 pi and so on. So this is the contour plot for G. We can also specify the number of levels. So I don't know that we have, so this contour plot for G, that we should have the 20 lines. But probably we don't really have 20. 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe we only see 9 or maybe 10. So the horizontal lines are also contour plot. So maybe only 10 lines. So I don't know why we haven't seen 20. Maybe we don't have enough space to write this line for this part, or maybe, yeah, probably that's the case. And also we can make an image of XY, FXY by this heat map. So you can see we don't have any legend, but the thicker color means higher value. So 10 square plus 10 square is 100. So this color means 100. And this 8 by 8. So this color means 64, or 2 times 8 is 16. So this means 16, and so on. Actually, this 1 times 8 has the same color. So this is actually the discrete, and probably this color is assigned for maybe, I don't know, maybe 7, maybe 8 to 20 or something like that. Yeah. And another one is 3D graph with this lattice. So you can see this is x0 is y is 0. And okay, so this is x-axis, horizontal. So y, the vertical axis is y. Actually the vertical is f of xy, and the other direction is the direction for y. So we can make this 3D graph. Yeah, you can search on the internet, then you can see many other graphs. So the PC monitors are anyway 2D, so it's hard to see what this means. But yeah, also the R has some option to dynamically rotate graphs, so that we can see exactly what this 3D graph is. So this is relatively simple, so we can imagine the shape, but yeah. And what? Yeah, that's it. And the next one is the graphical and numerical summaries. So we use this ISLR package. So this package was developed by the authors of the textbook. And this data set is the auto data set. So we have the 392 different types of automobile, different models of automobile. And each line is a model, and it has some specification, such as the mile per gallon, the fuel efficiency, and the number of cylinders, displacement, horsepower, weight, and acceleration, year, and origin. Origin is either Europe or Japan or US. So the category and the name. So AMC Ambassador Brougham. I don't know this car, but these are 7 these data set. So I don't really know these cars. And we can make a box plot. We can make a scatter plot first. So this is the plot for the number of cylinders and the mile per gallon. So number of cylinders is an integer. So either 3, 4, 5, 6, 7, and 8. Sometimes maybe 10 or 12. I haven't seen 7. I heard that for airplanes, the number of cylinders is always an odd number because sometimes the engine stops when the number of cylinders is even, because it is like the V engine, V-type engine, V-shaped engine, sometimes stops if the number of the cylinders is even. Also straight one. So anyway, so the cars have the either 4 or 6 or 8 cylinders. So anyway, this is the discrete 1, 2, 3, 4, 5, the box plots. So if we just plot, this becomes scatter plot. But if we make cylinders as factor, because this is discrete scale, then we can use the factor variable here and the continuous variable here. Then we can make a box plot. So 3, 4, 5, 6, 8. So 7 is ignored because this is just factor. So we have 5 levels. So numeric, I mean, the meaning of these numbers are ignored. Also, we can change the width of the cylinder, the width of the box plots. And now the width is proportional to the number of observations. So you can see that only a few cars have the 3 or 5 cylinders. So the 4, 6, 8, it's wider. So these are box plots. So the 50% of observations are within this box. And this is basically the 1.5 times this height of box from this upper side and lower side. But this is censored at the largest observation. So this is not entirely symmetric. Actually, no observations below here. That's why this so-called whisker ends here. And these circles are outliers. More than 1.5 times interquartile range from the upper side of IQR, upper side of, the third quartile, so 75 percentile. The thick line is the median. Sometimes we want to put the box plot there horizontally, and that makes this. So you can just specify this. And box plots are useful to describe the relationship between categorical and continuous variable. And how about continuous versus continuous? That is usually described by scatter plot. There you can see this. For example, MPG and the displacement have negative relationship, but not linear. Obviously, we have some curvature. Obviously, MPG cannot be negative, even if the engine is infinitely large. So it's natural. And some relationships are almost linear. For example, displacement and horsepower. I'm not good at physics, but it's somewhat reasonable. And these are redundant information. So this information and this information. So these two planes should be identical. So just its two axes are interchanged. So if we flip this, then this becomes this. It looks different, but actually the same. You can see this point. Sorry, I think some lag. So these 2 points corresponds to these 2 points. Yeah. And if we use the ggplot to package, then we can make more fancy graphs. So this is correlation matrix between observations. You can see MPG and the acceleration have very high correlation. Maybe probably we have some option to show this legend, but the thicker color means the higher correlation. And horsepower, displacement, and weight have the large correlation, but not as large as MPG and acceleration. And the yellow ones are probably the small, negative ones, negative correlation. So MPG and, for example, MPG and the horsepower, usually they have negative relationship. The larger horsepower, especially the larger displacement, means lower MPG. And this is dendrogram. So if we want to group these variables, which variables should be grouped first? And the conclusion is that we have to group. Actually, we have to group the weight and displacement first. I forgot the exact criterion to group variables. So how to group variables. Yeah, I think that probably correlation. Yeah, so the displacements, we cannot really see, but the correlation between weight and the displacement is largest. Sorry, this diagonal line is just, yeah, probably this is not correlation. So diagonal line should be correlation equal to 1, but the colors are different. So probably something different.
Okay. I was wondering why they should be the same color if they correlate by themselves.
Probably they use the covariance or something. The scale matters for this. So I'm not exactly sure why this appears like this. But probably this is covariance rather than correlation, because you can see that this color is probably slightly thicker than these colors. Right? So, but you can see if we see the difference between this one and this one. So the color difference is larger. So that means the difference in covariance is larger. So correlation is probably slightly smaller than this. So here, these 4 panes have almost the same number. So probably they use the covariance. So this is a kind of annoying. So I think this is a little bit strange. Yep. Yeah, probably covariance. So that in terms of correlation, this and this are closest. Then next this, and next this, and these 2 and these 3 are different. Actually, negative relationship. Yeah. And also that when we use the GG-ALI library or G-GALI library, I don't know. But if we use this library, then we have fancier figures like this. So this gives correlation. And yeah, you can check. So what's the highest correlation here? Highest correlation is displacement and weight. Highest correlation, displacement, weight. So they used correlation for this dendrogram, but to determine colors, probably they use covariance. Yeah, probably they use covariance because the most computer scientists at first, the standardized data. So if you want to see correlation coefficient, then just you can standardize data. So then covariance is more general and convenient in some way. And the next correlation is highest between horsepower and the displacement and the weight, and some test restars means what? Maybe p-value of less than 0.01 or something like that. Yep. And scatter plot here and correlation coefficient between here. You can see displacement and MPG have large negative correlation. And actually all correlations are statistically highly significant. And these diagonal parts are the histogram of each observations, each variable. So MPG like this. So most cars have MPG of maybe 15 to 20. It's known that the car's MPG does not improve much over time because cars are getting larger and larger. So if we fix the specification, the MPG gets better and better over time. But maybe currently, yeah, but still probably our car's MPG is better than 70s. And displacement, the most displacement, power, this distribution, and weight, this distribution, acceleration, this. So some other ways, the correlation heat map here. And this is almost close to 1. And these are close to -1, actually. And this is between maybe 0.5 and maybe 0.3. Yeah. Yeah, and yeah, so this does not make much sense on this PDF file, but this scatter plot, then we can type the identify of this XY and the name of the cars. Then when you click on our graphics, you have to use the base R package, not through R Studio. Use the R package and you click this, then you can see the name. So this is interactive function, identify XY name. Yeah, so these are the contents in chapter 2 lab. So we will discuss the how to use R in lab session. But the chapter 2 that we only have the mostly conceptual things. So just I discussed these graphics. Yeah, ggplot2 has the textbook. So I think the textbook's title is ggplot2, and that has the graphics, the explanation of how to make the beautiful graphics in ggplot2 package. You can any questions? So most graphics can be done by the base package and also ggplot2 packages. If you use those two packages, then probably that you can make most of the popular graphs. Maybe you need ggally also. Okay, so do you have any questions? Still, we have 10 minutes, so maybe we can go to chapter 3. Stop sharing.
Professor?
Yeah.
In I've got a couple of situations. One of mine is in going to be running about R 4.2.0. Hopefully there's going to be nothing too tricksy in that one. I'm having some issues with getting my Linux back up. It broke. But I'll be running a older version of R on Windows. I don't think this should be giving us any grief. They should carry over for the most part, but I intend to get up and running shortly. Other than that, looking forward to it.
Sorry, other than that, what?
I'm fine. I'm just I just want to make sure there wasn't a minimum level of R or R Studio. That
I think the any version is fine. Maybe less than 3.3 or something, maybe different. But I think that mostly it's fine.
I'll be over 4. I'll be definitely over 4.2.
Yeah.
Thank you.
So as long as you can install the package, you are fine. So if your R is too old, usually you cannot install some packages, and that it makes the most of the troubles. Okay, so okay, so maybe we don't really go into the chapter 3, but okay, so maybe we review the chapter 6 and chapter 11 of the book. Stop sharing. Yeah. So we just want to review the chapter 6 and chapter 11 of 5030 so that we can review materials. Download 6. Yeah, so linear regression. So linear regression is this. So we observe the pair of x, y for n observations, and then we want to fit the straight line on the xy plane. So that is the linear regression. And our main issue is how to estimate A and B. So in general, in statistics, estimation is the primary issue. So given data, we want to estimate A and B. The probabilists there want to discuss something given A and B. Yeah, and how to determine A and B? That is by this. So suppose we have 5 observations: x1, y1, x2, y2, maybe x3, y4, x3, y3, x4, y4, and the x5, x5. Sorry, maybe I didn't share. Yeah, okay. So yeah. So then basically we want to minimize the sum of squared distance, vertical distance between this estimated line and original observations. So that means that if we change the role of x and y, then fitted line is different. So minimizing, horizontal distance and minimizing vertical distance is much different issues. So probably the horizontal distance is minimized. Maybe the straight line is like this. I think there is a theorem that I would say the B tilde and the B, the minimizing squared distance and horizontal distance. If we multiply these two estimators, then that is, I think, less than 1. So we have some relationship. Yeah, but the vertical distance, the squared vertical distance is minimized. And this is the good way because, okay, so squared distance is a natural measure, but also if you see this, the form, you can see this is a quadratic function of A and B. So it makes the parabola, if we think about the 3D space of A and B and the value of this SSRS, SS residual. So the parabola, obviously, we have the global, the minimum of this function, and we can estimate it pretty easily by, for example, Newton-Raphson method. So optimization is easy, or we don't really have to even use it. Just we can differentiate it, and the linear equation you can solve. So least square is good, easy, makes it easy to estimate A and B. So this is the linear regression, and actually we say this is linear. One reason is that this is a straight line, but that isn't actually essential. So this is a linear function of A and B. So that is the point. So then the squared distance becomes a function of square of A and B. So generally the linear model means the right-hand side is linear with respect to parameters A and B. Yeah, so that is the linear regression, and in terms of probability, then sorry, before that, we say X as independent variable or predictor and Y as dependent variable or response. But sometimes, X does not cause predictor and may not be the best word to describe it. So we only, consider the association between X and Y and not causation. And no statistical model proves the causation. So usually the causation is just defined by the time, the point difference. If X happens first and Y happens later, the people think X causes Y, but in other cases, basically statistical theory never prove any causality. So only association between X and Y. And probabilistically, the A and B are constants. So we don't know the truth. We don't know A and B, so unobserved, but these are constants. And X is the classically assumed deterministic. So these are constant, observed X. And epsilon is random because it's error. And Y is A plus big X plus epsilon. So constant times constant plus constant times constant plus random. So Y should be random. So epsilon and Y are random. And Y is observed, but epsilon is unobserved. So that is our interpretation quantities. So Bayesian interpretations are different. So usually X is random and A and B are also random, and so on. But so this is the frequentist, the classical approach, and this is the assumption in terms of probability theory. Yeah, and epsilon t is usually assumed the independent and identically distributed. So sometimes this is violated, but in such a case that we have a more complicated model, especially if epsilon t are dependent, it's complicated. Yeah, so this is the review of linear model. So maybe we continue review a little bit next time, then go to chapter 3. All of you have studied linear model before? I mean, if you are in Stat 5030 that you have studied, and I think they also 5800 covers the linear model, right? So have you, any of you have taken 5800 last year? No? Yeah, have you covered linear model?
5800s this semester.
I mean, last winter. I mean.
Yeah, I took it last winter and we briefly covered it towards the end, but
okay, not much, but still covered a little bit. Okay, yeah, great. Yeah, so then I think that all students know somewhat about linear model. Yeah, so next time that we go into more details of linear models. Okay, so I will post the quizzes tonight. So yeah. And see you next Monday. Yes, and there are some statistical the mathematics department colloquium this month by job candidates, and actually tomorrow we have a talk about some machine learning numerical analysis, so maybe more mathematical. And yes, and I think that January 30th, we have more statistical presentation. So maybe if you have time, that you can attend the seminar, in person in Nelson Library at 2:45 p.m. You the math department. Okay, so see you next week.